All right. I think that's the crew. Yeah. All right, sweet. What's going on, everybody? My name's Daryl Roberts. I'm the head of AI at a local AI company called obney.ai. We're doing lots of really cool things in AI. My background spans across data science, where eventually I made my transition into computer vision, working on projects like dental reconstruction in the 3D space, self-driving forklifts, things along those lines, as well as 3D printing for concrete houses. Eventually, with this big boom in LLMs like ChatGPT and Claude and all of those things, I found that I can't really get away from agents. They're not really going anywhere. These days, I'm working mostly with LLMs on a daily basis, and I wanted to share our design philosophy whenever we're approaching these things, because when it comes down to it, these AI systems are still a discipline of data science, and they've allowed for some... Oh, it's too loud. Okay. Oh, yeah. I do talk very fast, so hopefully I don't lose you guys. If I do, just be like, hey, slow down, man. But yeah, so it is our design philosophy for designing AI systems in a smart way that you can actually trust them. So let's go. I guess I have to be on this screen. All right. So first things first, do we have any veterans in the building? All right. We got one. All right. So happy early Veterans Day. That's it. So happy early Veterans Day. I myself was in the Marine Corps for 6 years, so very big part of who I am, and more importantly, tomorrow is the Marine Corps birthday, 1775 Ton Tavern. It's our birthday tomorrow, so hoorah, Devils. So in a very Marine Corps fashion, let's get off of that. In a very Marine Corps fashion, there is this decision matrix in the Marine Corps called the OODA loop. So what the OODA loop is, it's a principle for making quick decisions. It was founded by Colonel John Boyd, who developed this decision-making framework in order to help with fighter pilots, and it has become fundamental in how Marines think about rapid decision cycles. In the same tradition, on the back of the OODA loop, we have our AI engineering loop. So that AI engineering loop looks a bit like this. Originally you want to express your intent to the actual model. What's your data look like? How are you expressing that data? What do your prompts look like? Your processes and your logic, and we'll get into that here. But the general shape is we're going to express intent. We're going to allow our models to execute on that intent. We're going to observe the results, and then we're going to adapt our models and improve them. Here's a common pattern that we see a lot in, if I can say anecdotally, in consulting. We're seeing this sort of pattern that companies are adopting that's just the React plus MCP recipe. Do we have anybody familiar with React or what it is? Yeah, so it's the pretty common cycle. A lot of the big companies are using it just because you can throw it together and say go, right? So it's reason and act. Essentially, your AI is going to take a whole ton of tools. You're going to give it a toolbox of like tens of 20s of 50s of tools and give it some task and hope that it can carry that task out, and most of the time it can't, and you're given sort of something where you're thinking like this thing just doesn't work, right? So MIT did a study. They found that 95% of AI startups are actually failing. So we want to understand why is that. So the statistic's quite staggering. It highlights that there's probably some common missteps happening in the AI world. We see that React is just a recipe for failure. They typically are choosing some powerful general model like a GPT-5 or a Claude Sonnet 4.5. They're going to give it a ton of MCP tools or ChatGPT assistants with their own internal tools. They're going to just let it do that React pattern, reason, act, observe, repeat, and then they're going to build an app around it, and they're going to ship it and say that they have some magical AI application, right? So sounds familiar, but React won't be a winner. Here's why. It abstracts away your entire AI layer. You have absolutely no idea what's happening, and you have no idea of how to fix it. What happens when things go wrong? So you see that you basically have three options. You can improve your input prompt and hope that it works this time. You can try a different model and hope it does better. You can add more tools and hope for the best, and then you get a new result and you hope it's right. So you notice a pattern across all of these options. It's hope. It's not engineering. You have no control over the reasoning logic, which is hidden. You have no control over the query decomposition, which again is hidden. The search tasks are opaque. Your tool call decisions are uncontrollable. Your context compression is invisible. Everything is happening behind the scenes, and they're doing it for you and saying, I swear I'm doing it a very good job. and buy my product. You say, if my thing's not doing well, if my application's not doing well, then that just means that the model can't do the job, or this MCP server isn't good enough, and now you're stuck until something better comes out. You've abstracted away your entire AI layer. You have no levers to pull, no knobs to turn, and no systematic way to improve it. Then we see a fine-tuning rush, where a company says, okay, it's not doing the job right. I have terabytes of data. I'm just going to fine-tune my own model, right? Typically, when we come into a situation like that, the first question I ask is, what have you tried? Why have you decided that fine-tuning is necessary? What are your metrics? What is your faithfulness metric, your context recall, context precision, etc.? How did the pre-built models perform? How well-defined is your workflow? Is your data even ready for fine-tuning? Have you tested simpler approaches like better prompting, few-shotting, or retrieval? Fine-tuning, we find, is the most time-consuming and the most expensive operation that you could possibly run on AI, especially on these much larger models. If we're going to fine-tune, we want to be 100% sure that it's necessary, and we want to be 100% sure that the data is quality. But most teams jump to it because they don't have a systematic framework of improvement, and they don't know what else to try. So we're no longer in this era of data science where we see an AI problem, we collect a massive training data set, we build a neural network, we tune the activation function, the learning rates, the hyperparameters, or even gradient descent. We're not training from scratch anymore. But this has led to irresponsibility. So teams think that just throw GPT-4 at it and it'll figure it out. Prompts are easy, anyone can write them, and we don't need machine learning engineers anymore. This is wrong. So at the end of the day, this is still a data science discipline, and these probabilistic models still need to be tested for if they solve your problem. They still need to be measured as far as what does success look like for you. They need to be quantified, and they need to be improved. You can't improve what you don't measure, and you can't measure without a plan. So we introduce our loop framework, our AI engineering loop, where we have express intent, execute plan, observe your results, and adapt. You notice that the loop closes between adapt and express. And this is because the better your system is adapting to your data, the better it is that you're able to express what is your intent. It's able to do the job more reliably. You get better specifying you get better at specifying your intent based on what you observe and what you measure. And this is the loop that separates engineering from consumption. And that's the separate, right? So you have AI engineers that are doing loops like this and improving models, and then you have API consumers, which are essentially just doing express, where they say, I want my AI app to do this thing. They do execute, where they say, I want a model that's good at doing that thing, and then they release it, right? So they don't do anything else. So that's what separates us. They just pray to the AI gods above that it's going to work. Organizations that execute this loop systematically will dominate. Those that don't will likely be part of that 95%. So express is more than prompts. Express is how you specify your intent, and your intent can be consolidated in many different ways, right? So it's more than just writing a good prompt. That's part of it, but expressing is much broader. It includes your data preparation, so your parsing strategy, your chunking strategy, cleaning and metadata. It includes your architecture design. Are you using RAG? Are you using agents or something hybrid? What is your process flow? So are you doing multi-step reasoning? What's your tool orchestration look like? And intent specification. I will preach DSPy until the day I die or until something better comes out. So I'm a DSPy shill. But DSPy signatures give us the ability to go back to engineering and less prompt hacking. So just because there's a new shiny tool doesn't mean that you need it. So data preparation, parsing is how you actually express or show that your data or what shape you want your data to be in. So you may make the choice that maybe Markdown's doing best for your use case. In some cases, maybe HTML's doing best. So you decide, I'm going to parse everything to Markdown. I'm going to use PyMove PDF for LLM. And it's performing better than plain text extraction. Just remember at this step, garbage in, garbage out. So parsing quality determines everything. Chunking. So chunking is how you say, okay, what is a meaningful unit of information for me? The trade-off is larger chunks have a tendency to come back more accurately, so you have a better recall. But the larger your chunk, the larger your context window, so your precision's lower as well. So you have that trade-off that you're trying to measure. Then techniques. Are you going to do fixed size chunking? Are you going to do recursive text splitting? Are you going to go towards something more difficult to set up like semantic text splitting or even agentic text splitting? Our surprise on this one that I'm kind of mentioning here is after running all of these things and setting up semantic text splitters and agentic text splitters, at the end of the day, we got best context and recall precision if we just said, take the whole page, right? And we wouldn't have known that if we weren't measuring it. And then cleaning, you need to clean out your HTML tags, your headers and footers, your sentence segmentation, paragraph reconstruction, lowercasing, Unicode, all of those things. You need to deduplicate. So how are you deduplicating? Are you doing exact deduplication, fuzzy deduplication, or semantic deduplication? And then normalizing text to consistently embed them so that you can have your better retrieval. So your chunks express what is a meaningful unit of information to me, how you clean expresses what you consider in your data set to be signal versus noise. And then these are the technical details. They are design decisions that affect your retrieval quality. And then intent specification. So again here, I'm going to push DSPy a little bit. So it takes you from prompt hacking to actually back to engineering. Some of you this may look familiar to you. You're an expert assistant. Please analyze this carefully. Your job depends on it. Depends on getting this right. I'll tip you $10,000 if you succeed. Think step by step. You're a pilot in Star Trek specialized in math, right? And now all of a sudden it can solve the problem, right? So DSPy takes that and takes us back to engineering. So that way we can specify, I'm going to give you these inputs and I'm expecting you to give me these outputs in this shape, and this is exactly what it is. And what DSPy is doing is it's actually prompt compiling in the background with a compiler that's actually able to adapt. It's built on Stanford scientists' research in their design of optimizable instruction templates, and DSPy replaces prompt strings with declarative signatures. So execute. So execute is what most people think is AI. This is all of AI, right? So model selection. Which model am I going to use? Orchestration. Am I going to be using simple retrieval? Is it just purely generation? Agent execution, and swappability. When I say swappability, I say that because we always want to design our systems in a way that we can very easily swap a model. If you build your app around GPT-4 and then GPT-5 comes out, now you need to go back through all of your code and fix it. Maybe GPT-5's output format's different, so now you have to go change all of your pre-processing. You need to change how you read its outputs, things like that. So always design in a way that swapping is easy, because again, over this entire loop, we're going to be figuring out and actually measuring which model is performing the best. And if we lock in, we can't measure anything but one thing. So again, here just harp on engineering in a post-AI world, if I can. Yeah, there we go. Hugging Face, again, just to harp on the, I guess now it's not going to load. Well, there's over 2 million already trained pre-built models on Hugging Face. The MTEB leaderboard has a multitude of embedding models separated for particular use cases across law, finance, or pretty much anything you could possibly think of. The chances are, if you have an idea for some generative model, somebody else has already trained one, and your job is more about going and finding the right one, measuring if it does right for your task, and if it doesn't, throw it away. Go find a different one. OpenRouter also holds tons of models that it's essentially like a routing service. We use it heavily. It gives us the ability to very quickly swap between models by just changing a single string. And then even Ollama, most of you are probably familiar with that if you want to pull down models locally. So our choices are vast. Our job is no longer about building a model, it's about wielding them effectively. I know I'm bringing up RAG a lot. It's probably one of the most common things that a lot of you have heard of or most people are familiar with. There's obviously a lot more than RAG, but just to give you a concrete example, we can see that there's a query input of a user saying, how do I reset my password? Then that query is embedded with sentence transformers. In this case, we do a search over the vector DB. We execute top 5 similarity search. We have to make some decision there if we're going to be doing dense search, sparse search, or hybrid, or even self-query retrieval. We need to re-rank it with some sort of cross-encoder and then generate an answer with whatever model we have chosen. Each step in execute, you're wielding multiple models and orchestration. So you have your self-querier, you have your embedder, you have your sparse model, whether you choose BM25 or Splade, and you have your cross-encoder, or am I using Coheres or somebody else's, and then your generation model, which LLM am I using, right? So it's not about abstracting away your entire AI layer to OpenAI and letting it do all of those things for you. It's about wielding each of those models and being able to be accountable for each one. I did want to highlight here, retrieval does go beyond just like splitting a PDF and going and retrieving it, right? Just as an example, we have KNN few shot retrieval, which is about retrieving examples. So a lawyer comes in and says, what laws apply to my case on traffic law? What laws apply to my case, blah, 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 violent something, right? So what KNN few shot is doing is, instead of embedding the query to go find a good document to fetch back, it's actually embedding your query and going to your data set to find other similar questions that other lawyers have asked, and finding really good examples of when lawyers said, you know what, that's a really good answer. So now we're providing the correct few shot prompts or few shot examples to the actual context, so we can be happier that, or more confident that our answer that's coming back looks like the answers that lawyers have been happy with before. So it finds similar questions that are rated high among satisfaction to your users, provides those question answer pairs to the context, steering the model to give similarly impressive answers without flooding your context with irrelevant examples. So retrieval is everywhere. It's not just RAG. It's for selecting examples. Yeah. What's up?
Sorry, is that K nearest neighbors or something like a knowledge?
Yeah, so that one's K nearest neighbors. Yeah, yeah. It's actually provided in DSPy again, chill, but yeah, it's really great. So yeah, it's not just about RAG. It's selecting examples. It's finding relevant context in your data store, user memory with tags, company policy, legal information, or a number of things. However you need to put information into a context window, that's considered to be retrieval. So observe. So observe includes whatever observability tool you choose to use. Our favorite is LangFuse. It is an open source library that you can pull down locally. You don't have to trust anyone or a cloud service or anything like that. They do have a cloud service, but it does give you the option that if you want to pull it down and put it in a self-hosted container so your data doesn't go anywhere, you totally can. It gives you full tracing, so you can see reasoning behind the scenes, decisions, tool calls. You can get a look at the metrics like tool usage, latency cost, and debugging, like where do things go wrong. In an example, we could see this one here is a code agent that we worked on a little while back. And we can see with observability, we actually get a chance to look at the entire process and see where did things actually go wrong. So if I put in a question and I get a really bad answer all the way down here, I don't think that my entire thing is trash. I can actually go through this and see we made the right decision here. And then whenever I got here, when the model said, I don't think you need to look at the commit logs to understand what this user's asking about, and now everything else downstream is incorrect because it made the wrong decision here. You no longer need to go fix everything. You can go take this one, put it in your data set, make a correction, train that step, and now have more faith that the things downstream are actually doing their job correctly. So LangFuse may show in your traces that you're getting irrelevant documents. Maybe you can then see that the problem that our system is having is its retrieval quality. So instead of fixing my entire thing, I can choose a new embedding model, choose a new chunking strategy, something along those lines. I just know that my retrieval system needs to be better and my generation is probably fine. So the big six RAG metrics that are going to be the most common for pretty much any AI application are going to be context recall, which is did we receive the relevant documents? Context precision, are the retrieved docs actually relevant? Context relevance is how relevant is the context to the given question. Faithfulness is the answer grounded in the retrieved doc, so it's your anti-hallucination meter. Answer relevancy, so does the answer actually address the question that's being asked? And then answer accuracy, so is the answer factually correct? You need metrics at every single level. So you're going to have metrics at your retrieval for going to get the right documents. You're going to have metrics at your generation for anti-hallucination. You're going to have component level metrics for tool decisions, knowledge retention at multi-turn conversations, and things like that. You always want to put the right metrics in the right place so that you have full observability, because you can't fix, again, what you can't see. And you'll actually know where to improve your pipeline. So adapt. This is where your loop closes. It's the systematic improvement of your model, and here's where the actual magic happens. This makes actually the difference between using AI and engineering AI systems. So adapt includes evaluation, so your metrics, your benchmarks, and your tests, your analysis, finding failure patterns in your edge cases, optimization, so you can improve your prompts, examples, and architecture, evolution down the line for fine-tuning and retraining, and feedback to the beginning of your loop at express. You get better system design and loop closure. MyPro V2 optimizer, for example, is a optimizer that would be in this adapt cycle. It takes a look at your metrics, it takes a look at your actual modules and all of your training data. It will build an idea of what you're actually trying to improve on, and it's going to generate task-aware instructions that it's going to spread across a teacher and a student model that it's actually trying to improve. So here's some real optimization results that we do in the class that we actually just taught to some 16 engineers at a development company. And this is one of the examples that we actually go through. This illustrates just a really simple task for an LLM. We ran GPT-4o Mini across a Twitter sentiment classification data set where the output we were expecting is just negative, neutral, or positive, right? So GPT-4o Mini, straight out of the box on this data set, performed at 74% accuracy. So our first step was, can we improve the examples to improve our outcome? So we had a few things that we wanted to try. So we tried few shotting, or labeled few shot, which is random examples. It's essentially what you would do if you were writing a prompt yourself and you just wanted to put in some examples. Here's an example tweet and it was neutral. Here's an example tweet and it was negative. We saw 0% improvement by giving it just random examples. Doing a bootstrap few shot. This is for quality filtering, so you actually have a model that's going to go over your entire data set, find what likely are the best examples, and then put those into your context. And we saw about a 1% improvement. And then for few shotting bootstrap with random search, this is our more complex method. This will go through your data set. It will choose 4 or 5 examples, try them, see does the accuracy go up or down. If it goes down, it tries to explain why it went down and find examples that are better. If it goes up, it tries to explain why it went up and find examples similar to the ones that were successful. And you can run that on multiple epochs. After we ran that for a while, we only saw about a 2% improvement. So again, not amazing, but some improvement. And then finally, we did K&N few shot, which we just talked about a little bit ago. So the downside of K&N few shot is it will run every single time you run a query. So it's populating examples in the context at runtime, as opposed to bootstrap few shotting. You would pick your best examples and then those will permanently be in your context. But K&N few shot, we saw the biggest improvement at 4% jump for our few shotting. So we say maybe in this application, latency isn't the highest thing that we're worried about. Maybe it's a background process or something like that, where we can afford a loss in latency for a boost in accuracy. Then we moved on to instruction tuning. So this is where you take it from take this context and give me an answer to something that's more optimized in instructions. The example we had was the base instruction was classify the sentiment of the given tweet, and the optimized instruction that we ended up with was analyze the following tweet, classify its sentiment as either positive, negative, or neutral, consider the context, any subjective language and potential presence of sarcasm or internet slang. Provide only a sentiment label, positive, negative, or neutral, as your response. We didn't have to go in and beg the model to do what we wanted. We just gave our data set to our CoPro instruction optimizer, and it went and did that for us. And what we got back was a tuned instruction that we can point at and say, with that instruction, we got a 6% improvement, right? So we can actually quantify that things have gotten better. We just don't feel like they did. And then after that, we went ahead and did some model fine tuning. So now we have the perfect example and the perfect examples and the perfect instructions. Now we can take that and go and fine tune a model, distill those things into its weights, where we saw another 5% boost by fine tuning GPT-4o Mini. And then we show the students how you can keep this loop going by hooking up MyPro V2 to the Bootstrap fine tune. So periodically, it will continuously fix its instructions and then fine-tune itself, and then fix its instructions and fine-tune itself. And on the first iteration of that, we saw another 1% improvement. I can't imagine that we do much better than 90%, but maybe we see incremental steps towards that. But we can see by just basically fixing the prompt, by giving it good examples and good instructions, we took it from 74 to 84, and then we got an extra 5 by fine-tuning with the correct data. So again, 8 optimizer types. So labeled few shot, we covered these, are your random selection, quality filtering, and things like that. The one we didn't cover is JEPA. This did come out after we taught the class, but it has been an obsession of mine lately. It's more of a genetic algorithm for LLM reflections. Without going too deep into that, I highly recommend the paper. It's great. Big improvement on MyPro V2, and helps us with instruction tuning and finding few shot examples. let's walk through a complete loop. So theory is nice. Let's make it concrete with a real world example. And I'm going to walk through the complete loop of a real RAG system and what it might actually look like for you. So in round one, we have Mr. Customer comes to us and says, I want a customer support chatbot. So let's hand wave all of the pre-processing parts that have happened before here. So if you can imagine, their company's data is probably spread across hundreds of gigabytes of emails to customers. They likely have policy manuals. They perhaps even have some FAQ sheet that an administrator's holding in their personal computer on an Excel document. All these would need to be parsed, cleaned, have their metadata extracted, and make their data readily available for a single multi-use format. Some design decisions we come into on round one is we're going to do basic RAG, so we're just going to do retrieve and generate. We're going to use an all-many LM model, which is a very small embedding model at 384 dimensions. We're going to just chunk at 500 tokens per chunk with no overlap. Our retrieval strategy is going to be top 5 similarity search. We decided we're going to use hybrid retrieval. So for our sparse retrieval model, we're going to use Splade. Is anybody familiar with Splade? No. Is anybody familiar with BM25? No. It's essentially like keyword search, right? But Splade is a little bit deeper than keyword search. So words like car and automobile would be closely related. It's on the outside of the tokenizer. What it'll typically do is the next word of my cat ran, after the word my cat, maybe the word has a high probability of being the word ran, but Splade checks all of the words that have a high probability of being in that space, in that mask space, and it's going to search across all those words. So it's taking a step further than keyword, but it's not going all the way to the semantic space. Then we have standard dense retrieval on an HNSW capable database. That's just PG vector essentially. It's graph walking, so you're not checking over all of your rows, you're just checking over the rows that actually matter. And then we're going to be doing hybrid weighted. 40% of the weights are going to come from the standard sparse model, and then 60% are going to come from the dense model. And then our prompt is going to be simple. Based on these documents, pass in our context, give us an answer. So here we've expressed our intent. We want a RAG system that can answer customer support questions. So execute round one. So user inputs, how do I reset my password? We go do some retrieval. We search the database. We find the top 5 chunks. Then we have GPT-5 who's going to generate an answer. The system runs. It looks decent. You can reset your password by clicking blah, 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 right? This is where most teams stop.
Would you say this is equivalent to like the OpenAI assistant workflow or the assistant API workflow?
This is exactly what OpenAI is doing, yeah. So what OpenAI is doing behind the scenes, if you just say, spin up an assistant and I'm going to give you some PDF documents, OpenAI is going to do it the same way every time. They're going to create a 1,000 or 2,000 token length chunk that you have. It's going to be a recursive text splitter, so you have no control over where those splits happen. It's going to choose OpenAI embedding small or large for your use case, and it's just essentially going to do probably just dense search, maybe hybrid search. They're not too transparent on that, and you're going to get an answer back. So no control at all. So most teams stop here. They say, I feel pretty good about that answer. I have an AI app, and I'm going to make $1 million. But this is where us AI engineers go a little bit deeper, right? So now we're going to observe round one. And we look in length views, and we see our trace that came back with 5 chunks. Only 2 of the chunks were actually relevant and had anything to do with the answer. That's 40% precision. The answer we used was in both relevant chunks, so spread across 2 of them, but it missed key information that was in a non-retrieved chunk. So there's a chunk that's sitting in our database that our model never even saw that would have been critical for being able to answer the question correctly. So context precision's at 40% because 2 out of 5 of the documents were relevant. Our context recall is 67% because only 2 out of 3 of the documents we needed were actually retrieved. And our answer accuracy, therefore, is only 70% because we're missing some key details that our model never even saw. So our observation reveals the problem. Our retrieval quality is hurting us. So how do we fix our retrieval quality? So then we adapt. We do an analysis. So we see low precision is we're getting too many irrelevant docs. Low recall, we're missing relevant documents. And we just find that the root cause is our embeddings are not capturing our semantic meaning well for our particular domain. So we go on MTEB leaderboard on Hugging Face, or we go reach for another OpenAI text embedding model, and we say all many LM wasn't doing the job at 384 dimensions. Maybe we go wider. We go OpenAI's text embedding small at 1536 dimensions and see how that does. And we see improvement. And then we adjust chunk size. So we did have 500 token chunks with 0 overlap. Now we have 250 token chunks with a 50 overlap. That means that we're capturing our semantic meaning a lot more precisely. Smaller chunks mean that this small chunk is about this thing. It's going to be a lot heavier in that semantic space than the 500 token chunk. If you imagine the first half of it's talking about birthday cake and the second half of it's talking about the beach, your semantic space ends up somewhere in between, right? So we make those adjustments, and then we go on to see, did it make things better? So back again to Express, we've upgraded our architecture with a re-ranker. We now have an embedding model upgrade. We've fixed our chunking strategy. We now, instead of going for just the top 5, we go for a top 10. Then we allow the re-ranker to bring us down to a top 5, so it's the most optimal. And this loop feeds back to Express. We've improved our system design based on observation and adaptation. So now we go into round 2, right? So again, our users ask a question, and we observe. Now we can see that of our retrieval's doing well. It's getting about 80% precision. We're now finding all of our relevant documents, so our recall is 100, and the answer is complete. We feel pretty good about it. But now our metrics are showing us that our faithfulness is only about 72%, which means that 28% of the time, math is hard, we see that we're hallucinating. So our users are seeing some hallucinated, made-up facts that aren't in the context at all. So 72% faithfulness means that the model is either adding information not in the retrieved docs, or it's taking away or missing information that we wanted to see there. So now we move on to adapting round 2. So our retrieval quality, we want to keep it high. We're not going to touch the embedding model or our chunking strategy this time. But our generation is making unfaithful claims. We suspect that our root cause is a generic prompt doesn't constrain the model to the retrieved context. So then we run our optimizer on it, either MyPro v2 or CoPro. And we say we're targeting the faithfulness metric. MyPro tries a given 120 combinations, maybe in this case, selecting instructions that maximize that faithfulness score, grounding the answers in the sources. So now, instead of just giving this context, give me an answer, now we have an optimized prompt that says, you're a customer support assistant, using only the provided documentation below, answer the user's question accurately and concisely. Critical. Base your answer exclusively on the documentation. If the documentation doesn't contain the answer, say, I don't have the information in the docs. Don't add information from your training data. Then pass the documentation, the question, and you get an answer. I never had to go in and write this prompt. I never had to say, you're a Star Trek captain. It's now refining itself. We're getting more accurate instructions. We can be happy that our faithfulness went up because after the MyPro v2 loop, we got to actually see each epoch where we conditionally hill climbing to the correct metric. And we feel faithful that this is going well. And by the end of the training mechanism, we can see that our faithfulness hop on our data set went from 72% to 94%. So now our faithfulness is set. So again, we observe round 3. We send off another question, we get another answer, we see our retrieval metrics are doing well, we see our faithfulness is doing well, we're not hallucinating, but our HR department is noticing that our model is saying crazy things. There's some toxicity or some bias or we're checking for factual consistency. So we're seeing that our bias is a bit too high. We're seeing about in 15% of the answers, we're getting some bias. Toxicity at 2% is pretty low, so maybe we just leave that alone. And then in our conversational metrics, we see that our knowledge retention is bad, so it's not holding on to the context we need very often. And then for conversation completeness and context coherence, we feel pretty good. We're safe on toxicity, but bias detection shows at 15%, and knowledge retention across turns is only 78%. So now we want to fix those. So we adapt for round 3. Now what core metrics that we're optimizing for are going to be that bias and the conversational multi-turn memory. So for this particular turn, maybe we decide that before the answer goes to the client or to the user, we put in some sort of aspect critic. So a new DSPI signature that's going to actually look at the answer, tell you is it biased or not. If it is, then it's going to try and fix it and provide a new answer. And again, of course, that one's also going to have its own metrics put onto it as well. And then for the multi-turn context, maybe we decide that, hey, we're going to put a conversation manager in so we can make sure that we always have the most optimized context going into the context window. Instead of passing an entire conversation, we're only going to pass the bits of the conversation that the model really needs to know about to provide a good answer. We're going to track this across multiple turns of conversation and see if our metrics improve. So then our model now expressing at round 3, We have our architecture improved, our re-ranker, our conversation memory. We have a fairness constraint. We have an optimized prompt. We have few shot examples in there that are doing just right. Our bias detection goes down from 15% to 5%. Our knowledge retention goes up from 78% to 91%. And we maintain our core metrics for our precision, faithfulness, and accuracy. So this is across a multi-dimensional optimization loop. We've improved safety and conversation without degrading performance. Now, this is where things get fun, right? So now all those companies that said, day one, I want to come in and I want you to fine-tune a model. We're looking at 6 months later, we now at this point have tons of data that we've measured across all of these metrics. We know that the model's performing very strongly on all the metrics that we care about, but now we've realized GPT-5 is a bit of a bottleneck. At a cost at $15 million per, or $15 per million input tokens, and $120 per million output tokens per query. So every time a user uses our system, it costs 15 cents. And also the user's waiting on average 210 seconds or 3.5 minutes per query. Our monthly volume is about 100,000 queries per month, meaning that our monthly cost is $15,000 in API costs. And our users are waiting over 3 minutes for answers. So at 1 million queries a month, this would scale like crazy. So imagine your app blows up and you say, I'm going to be a millionaire, but now you have to give up half of your profit to OpenAI. So now what's happened during those 6 months, we've been monitoring, we've been saving all of our data and everything for our maximized metrics. We've collected 600,000 successful production queries. We have full traces with retrieval and generation. All of our metrics are tracked with retrieval generation, safety, and conversational memory. We have user feedback with thumbs up or thumbs down corrections. And we've found our edge cases where the system often struggles. Now we've naturally built this platinum level training data set from real production data validated by real users covering real edge cases. Remember when we said companies rush to fine tune without testing alternatives? Now at this point, we've tried everything else first, and now we actually have our data optimized and proven to be AI ready. In our first round of Adapt, we are going to fine-tune a model. Now fine-tuning makes sense. We've maxed out prompt optimization. MyPro's run 1,000 times at this point, and you're not seeing any uptick. Your few shot examples are perfect. You're not seeing any uptick. Your re-ranking, embeddings, and chunking is doing perfectly. Conversation memory is going well. GPT-5 is your only bottleneck. Now you know that fine-tuning is the right plan because we've earned it at this point. We have made sure our model performs exactly as we want, and now we think we can distill that into a much smaller model. So in this plan, we're going to try and fine-tune Quinn 3, which is a very small specialized model on our Platinum data set. With our target being, we want it to either match or get very close to GPT-5's quality at a fraction of the cost and latency. So why Quinn 3? It's only 5 cents per million input tokens as opposed to $15. It's 20 cents per million output tokens as opposed to $120. Average latency is at 0.33 seconds per turn, which is much better than GPT-5's average of 210 seconds. And then you can also self-host it. Now, if you have GPU clusters in your back pocket or something, you could put Quinn on your laptop and run with it, right? Expressing our intent in round 4 to production V2. Now we have a Quinn model that we've started fine-tuning to get it to fit along the lines of GPT-5. And we can see that while maintaining rough quality metrics, we can still perform at a similar level of GPT-5, but with a massive cost and latency reduction. And at scale, you can handle 10 million queries a month at about the same level that GPT could handle 100,000 or 600,000 a month, right? With a multi-metric scorecard, we can just see here between training GPT-5 for this task and then training Quinn 3 for this task. We see some realistic things. Our answer accuracy dropped about 2%, meaning that we took a small hit, but again, massive gains. Generation maybe improved a little bit because it's a smaller model and is better at this task. Safety maybe took a small hit. Conversational memory took a small hit just because the context window is more restraining. But we can see we go from 15 cents per query to 0.0003 cents per query. And then in production, we go from 210 seconds to answer a user question down to 0.4 seconds, with our monthly cost going from $15K to $30. Yep.
Would the latency reduction be made because you might have had a lot of steps in your previous one that
Not necessarily in this example. So in this example, it's purely the compute. So GPT-5 takes a really long time to reason and go through all of its things. Maybe it's a much, much larger model. It's a lot heavier that it has to go through that entire neural network, whereas opposed Qwen 3 is a much, much smaller compressed model, a lot less layers. You go from that first perceptron all the way to the end much, much faster than you can make it all the way through GPT-5's memory or network. Yeah.
I'm not sure I caught it. In that example, did you take those 600,000 real production user queries and you fine-tuned Qwen with that?
Correct.
Okay.
Yes, exactly.
So you did.
Yeah, that's our platinum level data. We have perfect instructions, perfect examples on 600,000 pieces of data. So instead of just like prepping data and saying, all right, now I'm going to go fine-tune Qwen 3, I now have 600 real use cases that I know are performing well and they're user verified, and that's what I'm going to use to fine-tune Qwen 3. So how do we embrace this loop? This is what executing the loop looks like. It's multiple iterations over time. Our retrieval quality in the end went from 40% to 80%. Our generation faithfulness went from 72 to 97. Our safety conversations, we can feel good about it. We checked over bias detection, toxicity. Maybe we even check in for summarization or factual consistency. We can also measure agentic patterns like tool correctness, task completion, and goal accuracy. And we've increased our production efficiency. So we went from spending $15K a month to $30 a month. Our latency went from 210 seconds down to 0.33 seconds with acceptable quality trade-offs. So notice what we didn't do. We didn't rush to fine-tune. We've tried everything else first. We started with a simple architecture and basic RAG. We didn't guess at improvements. We measured everything. We invested in observe early, laying fuse metrics from day one. We didn't blindly optimize one metric. We balanced quality versus efficiency trade-offs. We fixed problems one at a time. We fixed our retrieval, we fixed our generation, our safety metrics, and our efficiency. We didn't deploy and hope for the best. Please, AI gods, please. We had systematic iteration. We let production data guide our fine-tuning with 600,000 real examples. This loop is a systematic approach. It turns hoping into engineering. So how do you make yourself hireable as an AI engineer in today's post-AI world? Like I said before, things are less data science-y, less machine learning, and more about building real systems with real models. So if you want to break into AI engineering, here's what companies are actually looking for. They want to know that you can express your intent by learning system design, architecture patterns, engineering trade-offs, and data preparation. They want to know that you can execute. You can get fluid with pre-trained models like LLMs, embedding models, even APIs or orchestration of agentic work patterns. They want to know that you can observe. You can develop a data mindset with instrumentation, metrics, traces, and debugging. And they want to know that you can adapt, that you can master evaluation skills, testing, benchmarking, and systematic optimization. You don't need a PhD in machine learning to do this. You don't need to train models from scratch. What you need is a systematic way of improving AI systems. This is a new emerging discipline, and there's huge demand for people that can execute this loop. What to build and learn from here. So if you want something to try or you don't really know where to start, again, I'm a DSPy shill. DSPy is a must-learn for declarative AI programming. A Langfuse I highly suggest for observability, but there's tons of observability tools out there. Ragus and DeepEval for your evaluation frameworks. If you can show that you can also build an evaluation or a GEval with DSPy modules, that's also super useful. Vector databases, we use PG Vector. There's not really any need to go beyond that. But if you do find that maybe you prefer like a graph database or something like that, if you're going to use a graph database, that's a much more difficult approach. You better have tried the other ones first to see why did they not work for you before just going straight to that one. But PG Vector usually can get the job done, but there's the others as well, like Pinecone, Weaviate, Quadrant, Neo4j, or Falcor DB for graph databases. And then basic MLOps. Can you deploy models? Can you monitor models? Things along those lines. And then I have some recommended portfolio projects like end-to-end RAG systems with a metrics dashboard. Don't necessarily need to build the metrics dashboard. Langfuse has one built in, but if you can at least monitor your RAG systems, that's useful. Optimization case studies, so show before and after results of going beyond fine-tuning. multi-model AI applications such as text and images, along with tracing with those as well, and then production deployment with cost and latency analysis. Some things you want to stay away from are some common anti-patterns, such as stopping after execute, which we talked about, so building a system and hoping it works with no observation and no adaptation. Optimizing without observing, so adding complexity without measuring impact. Just randomly saying, I want to add re-ranking. Why did you add re-ranking? What was your retrieval quality before you added the re-ranker? Abstracting away control, so using black box APIs with no visibility. When things go wrong, you're stuck. Fine-tuning prematurely, so jumping into fine-tuning without trying something simpler. This is your most expensive operation, and it should be your last-ditch effort, not your first. And then having no systematic improvement. So trial and error, prompt hacking, let's try this prompt now, maybe this one will be better, without metrics showing that you're actually measuring if it's getting better or not. Just a slight push here. Our team is working in our free time on an open source library called Grain, where we have found that composing AI agents into behavior trees have proven to be really impactful. We also couple that with the idea of event sourcing, meaning that your system never forgets what's going on. So everything that happens, every button click is all saved in memory. And these models, if you've played with data science before, you know that if you assume what data is the most useful, you're introducing some sort of bias. By having event sourcing and never losing anything, you can always project the correct read model or the correct data in the right place for every node. And then we also are working to build in some JEPA-based evolution, but with the upgrade going beyond instructions and few shots examples, we also want the model to say whether it would do better if it had better data from the event store. So it's AI agents that never forget. Event sourcing equals perfect memory. You never lose anything. Every decision is traceable. No more black box react. Nodes will be able to evolve their own data access platforms. So an example mechanism for easily wrapping your head around something like this would be your initial state going into an agent would be it has access to your parts data to know when parts are going to arrive for a technician. It has a service schedule, so it knows what other jobs are going on at the same time. It even has access to the vehicle maintenance log, so it knows what vans are going to be available for a certain job. Our node discovers a manager keeps fixing the schedule because this mechanic's on vacation. So now the model says, you know what, if you had given me HR database data, I could then solve this for you so you don't have to step in as often and propose a new read model as well. Why this matters, again, it perfectly embodies the loop at watching at node level for self-improvement and things like that. So I'm not going to push that too hard. It's something that we're working on. It's a side project. It's not too deep right now. It's in very infant stages. But if you want to hop on, give it a star, check it out, definitely would love for you to do. So to bring it all back, we have OODA loop versus AI engineering loop. The OODA loop is our way in the Marine Corps of locating and closing with the enemy, observe, orient, decide, and act. As opposed in AI engineering, we now have the AI engineering loop for express, execute, observe, and adapt. AI engineers now produce this loop. Again, simplify and happy birthday, Marines. So 250th birthday tomorrow, hoorah. And today, we now have the AI engineering loop. So Semper Fidelis Marines and Semper Optimizing AI engineers. So appreciate you guys. So if you have any questions, here's my email. We're obney.ai. If you scan this QR code, it will actually lead you straight to GitHub on Grain. Yes, sir.
I was interested in that last part where you wait 6 months, you have 6,000.
Yes, sir.
Is that more of an operational task, or do you have an event where you're like, man, we've been studying these things, now we're ready to implement it? Or is that something that happens every 6 months, or do you start from I don't know. I guess
Yeah.
maybe
Like that process? Yeah, absolutely. We'll see often, like, we're hearing a lot from our users, right? So our users are saying, I'm getting a bad response here, or I didn't like this response here, which is usually a signal with the up or down thumb, right? We obviously, the better data would be you give me an up or down thumb and you also tell me why. But we can try and figure out why we got an up or down thumb. Why did things go bad? Someone on the back end, typically me or another engineer, may go through the actual traces and see, here's where the answer went in, here's where the answer came out, and this is where did things go wrong. So we can go through the whole trace and see, oh, we flooded the context with commit history where commit history wasn't needed. So there, instead of having it say, yes, commit history is needed, we instead go to that decision node and say, you should have said no here. and then we would add that to the data set because that's an example of where it did something wrong. Or in a more complex case, it provided the wrong answer to something, so we go in, we correct that answer. Then because it provided that wrong answer, that's a really good signal of something we need to train on further. So we'll add that to the data set. And of course, we don't want to put like just things it's doing wrong in there because then we'll overfit that way. But you also want to have like where it does something good. So if you see something, you're like, wow, that's really good. I really like what it did there. Add that to the data set as well. So you're just having this basically like this data set that's getting larger and larger over those 6 months of carefully curated examples of where you said it did really well at certain nodes, it did really bad at certain nodes, and instead of training an entire AI system to give you the right answer and hope that it's doing all the reasoning in its head correctly, now you can have control over every single reasoning step and say, I'm going to train just this one node, and you can be really precise with how you're training. Does that make sense?
Yeah, I'm more thinking like, does this get operationalized? Is there some sort of platform engineer who's going to be always doing this, or was it more
Yes.
like an event?
Yeah, you are doing this over time, yeah. So it definitely helps with those 600K examples to do 5 a day, 10 a day, something like that, rather than say, hey, we're going to set aside 2 weeks, everybody on the team come in, and we're going to label a bunch of data, because that sucks. But yeah, as you're going, like every day you come sit down, see, oh, my users asked these questions, I got some thumbs down, maybe I'm separating those another way, I'm seeing what those thumbs downs are and stuff like that.
I understand for a customer you put some sort of milestone. 6 months we're going to do this thing, but to get it really working, it's something that you never stop doing.
You're always planning for it, exactly.
So the point of these systems is to execute the intent of the people behind them, and so you have to take on a philosophy of monitoring that intent that you are always putting out there, and so it does become like a product backlog-esque version of this, where you're constantly refining that intent of your system.
It's a major change in the way most people write software.
Yeah, absolutely, absolutely, absolutely. It's not that big of a change from machine learning, though. If you've labeled like machine learning, like data science examples, or you go on Kaggle and get like huge data sets, like at this point, you need those things, especially if you're doing them in production, and you have no choice really but to create them yourself. Yes, sir?
Can you say something about like the decision matrix? So whenever you started introducing your DAP and you're building up new metrics, you started precision recall, then you introduced faithfulness and all of these extras and bias and security.
Yeah.
What kind of frameworks? And is that GSI or ML flow or their combination or maybe grain? But then let's say you decide, okay, our embedding model, we're not getting great retrieval, we think it's an embedding model problem, and you're going to choose a different embedding model. It means you have to re-embed all of your data.
Yeah, definitely.
And then run some tests, and now some of your metrics are going to go up and some are going to go down. So, like, how do you think about when you're teaching a 3-year-old to ski on the bunny slope? What are the bounds of that bunny slope, and how do you manage that over time?
Yeah, absolutely. A good question. Really great question. I say if you're going to go for retrieval metrics or any metrics really straight out of the box, I would go to a pre-built library like Ragus or DPVal. They've already done a lot of work, a lot of great work on training their own models that are good at these metric functions. As a judge. Yeah, exactly. So they've already done a really good job with that. I always say the end goal is to not rely on Ragus and DPVal and things, but if you do have your inputs and outputs coming out and Ragus is telling you this is a 0.72 accuracy, stuff like that, what I typically like to do is set up my own DSPy evaluator, and I'm going to train that DSPy module to perform just as well as the Ragus model, and now I have that one forever and I don't need Ragus anymore. But I will say straight off the shelf, reach for Ragus or DPVal, but always have a plan to train your own. And then on the second part, remind me? Oh, like some metrics are...
Like how do you weight which metrics you care about, not individually, but how do you think about making that decision?
Yeah, absolutely. I always, like what I told my students at the time, they were having the same problem, is now I have to re-embed all of my data and find out, like, are my metrics doing well or not? And it's a similar problem in data science as well, where the goal is to improve metrics over time, but you don't necessarily want to do it like on a very large scale every time. So what we'll typically do is have a curated sample of that data set and see how are our metrics performing on that sample. Does the accuracy go up or down? And what metrics do we care about the most? Typically, if you increase your chunk size, your recall is going to go up and your precision is naturally going to go down. We need to care about what is our bare minimum that we want precision to be at. What metrics do we actually care about the most? So if you're seeing a lot of hallucination, like you care about faithfulness probably more than you care about precision. If you are seeing things are getting wiped from the memory, and that's something really important, then maybe you care about that more than you care about answer accuracy or something like that. So you do have to weigh some of the metrics against each other. Obviously, the goal is to always hill climb towards the right one, but you do see that fluctuation. So what I typically say is grab a sample subset, see how a handful of models perform on that sample subset. Let me see if my internet will actually load. Oh, yeah, sorry. But yeah, does that kind of help?
Yeah.
Cool.
I have another follow-up. I'll find you after.
Cool. Sounds good. All right. I appreciate you guys. Thank you.